Vocabulary: statement, truth value, open sentence, domain, truth table. Symbols. A statement P is a declarative sentence with a truth value. That is either true, T, or false, F, but not both. An open sentence is a declarative sentence that contains one or more variables. Each variable represents a value in some prescribed set, called the domain of the variable. The open sentence becomes a statement when the values from the respective domains are substituted for these variables. An open sentence P of x over the domain S is when P of x is an open sentence and the domain of x is S. Also, P of x is a statement for each x in S, useful in the quantified statement section. 2 times 3 equals 6 is a statement. 2x equals 6 is an open sentence with domain integers. X equals 3 makes the open sentence a true statement. X equals 2 makes the open sentence a false statement. A truth table is the possible truth values of a statement listed in a table. Since there are two possible values for each statement, a truth table involving n statements contains 2 to the power n possible combinations. A truth table for the two statements P and Q is the following. Vocabulary: negation, not, disjunction or, conjunction and. Symbols. The negation, not P, is this. The truth table is the following. The negation is true if P is false. The disjunction P or Q is this, and the conjunction P and Q is that. The truth tables are the following. The disjunction is true if at least one of P and Q is true. The conjunction is only true if both of P and Q are true. Vocabulary: implication, conditional, if P then Q. Converse, biconditional, P if and only if Q. Symbols. The implication or conditional, if P then Q, is this. The truth table is the following. The implication is false only when P is true and Q is false. This truth table is by definition, but this following example could be helpful. A teacher says, if you're in class, then I'll post the notes. If P, then Q. When can you complain about a broken promise? P is true, Q is true. You were in class and the notes were posted. The promise wasn't broken, and so you can't complain. The implication is true. P is true, Q is false. You were in class and the notes were not posted. The promise was broken, and so you can complain. The implication is false. P is false, Q is true. You were not in class and the notes were posted. The promise wasn't broken, and so you can't complain. The implication is vacuously true. P is false, Q is false. You were not in class and the notes were not posted. The promise wasn't broken, and so you can't complain. The implication is vacuously true. For the implication, if P then Q, its converse is if Q then P. The biconditional P if and only if Q is this, which is the conjunction of an implication and its converse, if P then Q and if Q then P. The truth table is the following. The biconditional is true only when P and Q have the same truth values. Vocabulary: logical connectives, compound statement, component statements, tautology, contradiction. The symbols here are sometimes referred to as logical connectives. A compound statement is a statement composed of one or more given statements, called component statements in this context, and at least one logical connective. A tautology is true for all possible combinations of truth values. For example, P or not P. A contradiction is false for all possible combinations of truth values. For example, P and not P. Truth tables could verify above. Vocabulary: logically equivalent, inverse, symbols, theorems. If P then Q is logically equivalent to not P or Q. Statements are logically equivalent when they result in the same truth values. Using truth tables, we can show that if P then Q is logically equivalent to not P or Q. And we have the following. For the implication, if P then Q, its inverse is if not P, then not Q. A truth table will show that they're not logically equivalent. Theorems: commutative, associative, and distributive laws, De Morgan's laws, all verifiable by truth tables. Not if P then Q is logically equivalent to P and not Q. Not P if and only if Q is logically equivalent to P and not Q, or Q and not P. Commutative laws, associative laws, distributive laws, De Morgan's laws. Not P or Q is logically equivalent to not P and not Q. Not P and Q is logically equivalent to not P or not Q. With these laws, we can prove the following statements. Negation of an implication. Not if P then Q is logically equivalent to P and not Q. Negation of a biconditional. Not P if and only if Q is logically equivalent to P and not Q, or Q and not P. Not if P then Q. Logical equivalence. De Morgan's. Double negation. Not P if and only if Q. Biconditional. De Morgan's. Negations of implications. Vocabulary: quantified statement, quantification, universal quantifier for all, existential quantifier, there exists, characterized, characterization. Symbols. An open sentence P of x over a domain S becomes a quantified statement through quantification by using the universal quantifier for all and the existential quantifier there exists. The negation of the universal quantifier is the existential quantifier, and the negation of the existential quantifier is the universal quantifier. Not for all x in S, P of x, is logically equivalent to there exists an x in S, not P. Not there exists an x in S, Q of x, is logically equivalent to for all x in S, not Q. A concept is characterized when we have this characterization. For all x in S, P of x if and only if Q of x.